Hello, and welcome to the ACM 2020 Turing Lecture, Abstractions, Their Algorithms, and Their Compilers. I'm John Hennessy, Professor of Electrical Engineering and Computer Science at Stanford, and the co-winner of the 2017 Turing Award with Dave Patterson. In all of its activities, ACM is guided by core values that drive innovation. ACM enables technical excellence through its support of global conferences that draw top experts on a broad spectrum of computing topics, and through its digital library, which is the world's most comprehensive repository of computing literature. ACM also provides support for growth of skills and knowledge, including curriculum development and resources for lifelong learning. ACM emphasizes ethical computing through its Code of Professional Ethics and Conduct, which is a collection of principles and guidelines designed to help computing professionals make ethically responsible decisions. ACM also has a commitment to diversity, equity, and inclusion. ACM recognizes that the contributions of all individuals to computing and strives to provide a welcoming environment that encourages full participation of people from all backgrounds and experiences. This diversity of viewpoints and reasoning is key to driving innovation. Before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. If you have questions for either speaker during this talk, please type them into the Q&A box at any time. I'll try to organize the questions as our speakers are talking, and we'll try to get to as many of your questions as possible. I also need to let you know that this session is being recorded and will be archived. You will receive an automatic email notification when this recording becomes available. Today, we present the 2020 Turing Lecture by ACM's most recent Turing Award recipients, Professor Emeritus Alfred from Columbia University and Professor Emeritus Jeffrey Ullman from Stanford University. In addition to the Turing Award, both of our laureates have received numerous other awards. For example, both are members of the National Academy of Engineering and the American Academy of Arts and Sciences, and both have received the IEEE John von Neumann Medal, but not together. Prior to Columbia, Al served for many years as the Vice President of Computing Sciences Research at Bell Laboratories, and Jeff Ullman was previously at Princeton before coming to Stanford. Although I have known Al and Jeff Ullman personally for about 40 years, my first encounter with them was through one of their very first books, the 2-volume series, Theory of Parsing, Translation, and Compiling. It was 47 years ago, long before the famous Dragon book was published. Shortly after I arrived at Stanford, the Dragon book appeared, and a year or two later, I began teaching the compiler courses at Stanford using the Dragon book as our main text. I always loved teaching that course, as it taught not only important insights into the process of compilation, but how a systematic organization of a complex piece of software could make the software easier to write, understand, and debug. For this presentation, the talks have been pre-recorded. There are 4 separate talks on 4 different aspects of their work. Following the talks, we'll proceed to the live question and answer session. Now, let's hear from our Turing laureates.
For the theme of our lecture, Al and I decided to focus on abstractions and the role that they play in computational thinking and CS in general. This subject was actually the theme of the last book Al and I wrote together back in the early 90s. That book was an attempt to catalog the important abstractions of computing and also to argue that theory and practice were 2 sides of the same coin. For example, recursive algorithms and inductive proofs were closely related. Well, examining abstractions and generation, later we came to the conclusion that we can distinguish at least 4 different kinds of abstractions, which you see listed here. And I will go over them briefly. Then Al will talk about the important abstractions involved in compiling. After that, I'll come back and talk about database systems and the abstractions that drive that field. And finally, Al will talk about quantum computing, its abstractions, and its prospects. Okay. To begin, common to every abstraction in computer science is a data model and some sort of programming language. That programming language could be C++, or it could be something very simple and specialized. Okay. While other fields have abstractions too, we believe that it is the existence of at least a rudimentary programming language and the ability to write programs of some sort that distinguishes our abstractions from others. So let's look at a simple example, the dictionary, a set with operations insert, delete, and lookup. The data model consists of a universal set and a subset S. Okay. The programming language, such as it is simply sequences of the three operations shown here. Insert puts an element X into the set S if it is not already there. Delete removes an element from the set, and lookup tells us whether an element is or is not currently in the set. For example, a compiler uses a symbol table to store the program variables that are accessible at any point in the program. So in that case, the universal set is the set of all legal identifiers for the programming language being compiled. Okay. When the compiler reaches a declaration of an identifier, you insert it into the symbol table, and when the compiler reaches the end of a scope, you remove all identifiers declared in that scope. When the compiler finds a use of an identifier, it looks up that identifier in the symbol table. Well, actually, it's a little bit more complicated than that. You need to store information about each identifier in the symbol table, such as its type, and you also need to deal with distinct identifiers with the same name, but let's not worry about that. So here's the cast of characters in the world of abstractions. We tried to break things down in terms of their intended purpose. Okay. What we call fundamental abstractions are intended to express algorithms of a limited scope and to enable us to study efficient implementations of basic processes. The dictionary we just discussed is a good example. Then there are abstract implementations like a hash table. These are ways to implement one or more different fundamental abstractions. We wouldn't implement a hash table just for the fun of it. We would only do so to support some higher level activity. Next, declarative abstractions are perhaps the most interesting. They're designed to allow programming at a sufficiently high level that we are really saying what we want, but not exactly how to do it. As a result, these abstractions require clever optimization if they are to be implemented at all. Two very important abstractions of this type that are used in compiler writing tools and elsewhere are the regular expressions and context-free grammars that Al is going to talk about soon. And in the database field, the relational model is an essential abstraction. And then there are computational abstractions. These are intended to model a real machine, either a bit abstractly, as with the random access machine model, or a conventional programming language, or precisely as with the instruction set of an actual computer. Now, let's look in a little more detail at the fundamental abstractions. We see two subclasses. First are abstractions that are studied and taught in isolation. We talked about the dictionary, but there are many other abstractions that you would find taught in a first course on data structures, for example, stacks, queues, and so on. And then there are more complex abstractions that are akin to a class and its methods, but without selecting an implementation for the methods. In particular, these abstractions are rarely considered in isolation, but are used in the context of a conventional programming language. Some good examples are trees and the graphs of various kinds. And to see what I mean by saying that the abstraction is embedded in a language, Suppose we're talking about some variety of graph, and the programming language for the abstraction has an operation that takes a node and returns the set of its neighbors. We need the surrounding general purpose language to iterate over the neighbors. That is, for each node in the set, do something. As I said, the purpose of abstract implementations is to support various fundamental abstractions. We talked a bit about the hash table. Lists of various types or search trees, balanced or not, are also common examples. But an abstract implementation is not yet at the level of the machine. And there are usually a good number of different implementations for these abstractions, each with different properties. For example, if you're an algorithms person, you think that the hash table is just great for implementing a dictionary. But if you're a database person, you worry about data sets that are so large that they need secondary storage. In this case, the important issue is how many disk accesses do you need? You would probably prefer a tree-oriented abstract implementation known as a B tree, a balanced tree whose nodes are entire disk blocks. So we'll talk about those later on. As I mentioned, declarative abstractions are those where you say what you want without having to explain how to get there. Okay. They require a sophisticated optimizer in order to produce a reasonable implementation. But once you have an optimizer, you've greatly simplified the task of writing programs in the domain that's covered by the declarative abstraction. A point that might not be obvious is that declarative abstractions cannot have a Turing-complete programming language. The reason is that once a programming language has the power of a Turing machine, it is impossible to tell what a given program is really doing. So you might get lucky and figure it out in special cases, but you can't write a general purpose optimizer. There are a lot of important examples of declarative abstractions. As I mentioned, when Al and I were working on compiler implementation, regular expressions and context-free grammars were very important as ways of describing the lexical analyzer and parser components, and having those pieces in the compiler generated automatically. In the database world, there's the relational model, and if we're interested in implementation of large-scale machine learning algorithms, linear algebra with its usual operations is another very important declarative abstraction. And last but not least is the computational abstraction. These closely reflect the machine, but there are actually many different things we might call a machine. Usually we think of a simple computer, which might be modeled by a typical programming language or by a more conceptual version of a machine, such as a random access machine or RAM abstraction. But there are also several varieties of parallel machines, ranging from a single parallel computer to an abstract parallel RAM model or computing cluster where an abstraction like MapReduce is appropriate. And we should also mention that there are computational abstractions for things that are not anything like a conventional computer, but that have their uses. Three examples of the Turing machine, which tells us what can be computed at all, but that no one wants to write code for. And then Boolean circuits are perhaps the earliest abstraction of use in computer science. And quantum circuits seem to be coming down the pipe as an abstraction of importance. So this diagram suggests how the concepts of abstractions, algorithms, compilation, and running time all tie together. We start with some abstraction, say the dictionary, just to be concrete. And then you might want to implement this abstraction in terms of a lower level abstraction, say a hash table. That abstraction might be implemented in a still lower level abstraction, and so on. For example, we might implement the hash table in Java code and then compile the Java to execute on the Java virtual machine. Now, you write some algorithm in the original abstraction. Okay, that algorithm needs to be compiled into the lower level abstraction. For example, if we start with a dictionary, then an algorithm is just a sequence of inserts, deletes, and lookups. Compiling to a hash table is simple. Say to insert X, you hash X and then insert X into the bucket given by the hash function. In our dictionary example, the first step of a dictionary program, such as insert 7, would be compiled into two steps. First, apply the hash function to 7 to get a bucket number B, and then insert 7 into bucket B. Similarly, for the other operations. Okay. And if you have a notion of running time for the lower level abstraction, that should give you the running time of the program in the higher level abstraction. In our example, actually, we don't have a running time for the hash table operation since we don't know how buckets are implemented. But once we implement the hash table, say in a conventional programming language, we get a running time for the hash table that carries over to a running time for the dictionary operations.
Hello, my name is Al Leho. I will now describe how the abstractions and algorithms that Jeff Ullman spoke about have transformed the field of compiler design from an art to a science. In 2006, Jeanette Wing wrote an influential paper in the communications of the ACM entitled Computational Thinking. In it, she said, computational thinking is a fundamental skill for everyone, not just for computer scientists. This paper stimulated a lot of discussion about the importance of computational thinking in education and more broadly in all fields of human endeavor. A little later, Peter Denning asked me to write a paper on computational thinking for his ACM Ubiquity Symposium. In it, I defined computational thinking as devising algorithms and abstractions with which you can solve problems using computation. This thought was present in the Foundations of Computer Science book that Jeff and I wrote in 1992. The first chapter of that book was entitled Computer Science, the Mechanization of Abstraction. In this talk, I'm going to discuss the impact that abstractions and algorithms, the two essential ingredients of computational thinking, have had on the field of compiler design. A compiler, as you all know, is a program that maps a source program into a semantically equivalent target program. If we open the lid of a compiler, we see that it is a composition of phases. Each phase transforms the source program from one representation to another semantically equivalent representation, often at a lower level of abstraction. This picture of a compiler has been the bedrock of compiler courses for 50 years. Each phase of a compiler has developed distinctive abstractions and algorithms over the span of this time. I will talk about some important abstractions and algorithms for the first two phases, lexical analysis and syntax analysis, and discuss the impact these abstractions have had on developing software. Let us examine the first phase of the compiler, the lexical analyzer. Its job is to read the source program character by character and to group sequences of characters in the source program into meaningful strings called tokens. Regular expressions are a declarative abstraction that are often used to specify the sequences of characters in a source program that constitute valid tokens. Following Jeff's definition of an abstraction, the data model for regular expression consists of sets of strings, and its operations are union, concatenation, and Kleene star. I've also shown two Unix-style regular expressions, one for integers, another for identifiers. There are several choices for creating algorithms to match regular expressions, patterns in input strings, choices with wildly different running times. One is the McNaughton-Yamada-Thompson algorithm. It constructs a non-deterministic finite automaton from a regular expression and simulates the automaton to find the regular expression patterns in an input string. The algorithm runs in time that is linear in the product of the size of the regular expression times the length of the input. This is a great algorithm for recognizing simple regular expressions. When Ken Thompson and Dennis Ritchie created the third version of Unix at Bell Labs in the early 1970s, Ken installed his regular expression pattern matching program grep on it. It quickly became one of the most popular programs on Unix. However, Ken's version of grep at that time did not allow union or parentheses for grouping. So I created a regular expression pattern matching algorithm I called egrep for extended grep that allowed parentheses for grouping and union as an operator to go along with concatenation and cleany star. I chose to implement egrep by first constructing a deterministic finite automaton from the regular expression and then simulating the deterministic finite automaton as quickly as I knew how. Once egrep had constructed the finite automaton, it was blindingly fast. It executed 3 machine instructions to process each character in the input string. However, constructing the DFA from the regular expression could take a lot of time, even because even the smallest DFA for some regular expressions could have an exponential number of states as a function of the size of the regular expression. Doug McElroy, the inventor of Unix pipes and recursive macros in programming languages, liked using egrep because it allowed union in regular expressions. However, when he wrote a calendar program that gave users great flexibility on how they could specify dates, he did not like the long time it took egrep to construct the deterministic finite automaton to recognize dates. The regular expressions he used for dates had an amazing number of unions in them. Using egrep to process these regular expressions was like constructing a Boeing 747 to fly across the street. You spend most of the time building the airplane and very little time flying it. So what I did was I created a second version of egrep that would construct the deterministic finite automaton state transitions only when they were needed. This dynamic version of egrep made the observed running time of matching regular expressions linear in the size of the regular expressions, plus the length of the input string. In particular, it made Doug's calendar program run very efficiently. In 1975, Michael Lesk and Eric Schmidt implemented a lexical analyzer generator they called Lex that would take a specification of a lexical analyzer and automatically construct a lexical analyzer from it. Lex used regular expressions to specify the syntax of tokens, and Eric Schmidt, as a young intern, put my regular expression pattern matching algorithm into Lex. Lex allowed users to create efficient lexical analyzers easily without having to learn the algorithms for efficient regular expression pattern matching. Lex and its descendants, like Flex on Linux, are still used today to build lexical analyzers, 46 years after the first Lex tool was created. Let's now examine the second phase of the compiler, the syntax analyzer, or parser as it is often called. The abstraction of context-free grammars, sometimes called BNF, is often used for specifying the grammatical structure of programming languages. Here is a context-free grammar for arithmetic expressions using the operators plus for addition and caret for exponentiation. Although easy to write, this grammar has a problem. It is ambiguous. The expression 1 plus 2 exponentiation 3 has 2 parse trees, according to this grammar. If we try to parse this input string using this grammar, using a bottom-up shift-reduce parser with a stack, after reading the string 1 plus 2 from the input and putting it on the stack and reducing it to expression plus expression, the parser encounters a shift-reduce conflict. It doesn't know whether it should reduce the E plus E on the stack to an expression or shift the exponentiation sign onto the stack. So here it has reached a shift-reduce conflict. To fix this ambiguity, we could replace this grammar with an unambiguous grammar for arithmetic expression. The grammar shown here makes the addition operator left associative, the exponentiation operator right associative, and gives the exponentiation operator a higher precedence than plus. It's also bigger than the ambiguous grammar. If we had operators on a dozen or more precedence levels, like many programming languages do, we would have to invent a dozen or more syntactic categories for the grammatical specifications of the language. This problem inspired Steve Johnson, Jeff Ullman, and me to create an augmented grammatical abstraction for specifying the syntax of programming languages that would allow a compiler designer to use compact descriptions of programming languages, but at the same time make them easy to parse efficiently and deterministically with a shift-reduce parser. We allowed compiler writers to use ambiguous grammars, provided they remove the ambiguity by declaring the associativity and precedence levels of the operators in the grammar, as shown on this slide. Using this augmented grammar and constructing a shift-reduce parser from it, it no longer has the shift-reduce conflict we had before, because the declarations before the production specify that exponentiation has higher precedence than addition. The parser at the point at which the shift-reduce conflict occurred previously has no conflict. It knows to shift the exponentiation operator onto the stack and trace out the second parse tree. Steve Johnson implemented a software tool called Yak to automatically construct efficient shift-reduce parsers from these kinds of grammatical specifications. Yak allowed compiler designers to write simple specifications for parsers for programming languages without having to learn the details of the algorithm for constructing the parsers. Yak and its descendants like Bison are still widely used today. I might mention it was Jeff Ullman who coined the name Yak. It stood for Yet Another Compiler. The details of these abstractions and their associated algorithms are discussed at length in a sequence of books on compiler design that Jeff and I co-authored in the span of several decades. The first book was published in 1977, and it had 600 pages. The second book in 1986 added Ravi Sethi as a co-author, and it had 800 pages. The third book in 2007 added Monica Lamb as a fourth co-author, and it had 1,000 pages. None of us had the right heart to write a fourth book. These books quickly became known as the Dragon books because all the covers had a drawing of a fierce dragon conceived by Jeff, symbolizing the complexity of compiler design. I might mention the Red Dragon book was briefly shown in the 1995 movie Hackers with a young Angelina Jolie. When my two children saw the movie, they for the first time thought their old man was really something. It shows you what it takes to impress your children these days. The impact of Lex and Yak and the abstractions and algorithms presented in these books has been substantial. They have transformed the field of compiler design from an art to a science. The first Fortran compiler built by IBM took 18 experienced staff years to build in the 1950s. In contrast, starting from the mid-1970s on, scores of innovative languages have been created in a few weeks using these tools and abstractions, and the Dragon books have been used for decades in universities around the world to teach compilers to generations of computer science students. Let me wrap up with a short story about my experiences teaching the one-semester compilers course to thousands of students at Columbia for the last 25 years. In addition to teaching the abstractions and algorithms used in compilers, I had the students form teams of 5 for a semester-long project that accompanied the course. Each team had to design an innovative new programming language of their own choosing and write a compiler for it. Many of the languages invented by the students far exceeded my expectations. One memorable language was called Upbeat. With it, you could put music to input data. The students illustrated their language by writing a program in their language that would play user-selected music triggered by user-specified patterns in the input data. They illustrated their language by taking the New York Stock Exchange ticker tape feed and having their compiled target program play music fitted to the patterns in the ticker tape data. When the market was going up, the music was bouncy and lively. When the market was going down, the music was gloomy and somber. Their theory was that a stockbroker would rather work and listen to music that would indicate which way the market was going rather than watching the ticker tape all day. I might mention that in the 25 years that I taught the compilers course, never did a team of students fail to deliver a working compiler for their innovative programming languages. I attribute this success to the abstractions and algorithms that Jeff and I documented in our compiler books and to the software engineering process that I learned by working 30 years at Bell Labs. So I conclude, abstractions and algorithms have transformed the field of compiler design from an art to a science. Thank you.
Now it's time to talk about abstractions that have had a major effect on the management of the largest possible data sets. I'll concentrate on the 3 examples shown here. Okay, first we'll look a bit at the disk-oriented abstraction, where you count only disk accesses. In this model, you sometimes draw different conclusions about how to do things compared with what is implied by the more conventional one level of storage random access computer. For example, balanced search trees, called B trees, look really good in this model, even though in the RAM model, balanced search trees are generally less efficient than a good hash table implementation. And more than any other, progress in managing large-scale data is due to uses of the relational model of data, so we'll focus on this abstraction. But there are also a number of important abstractions related to parallel computing. Shared nothing distributed computing has been central to a lot of research in database systems. More recently, MapReduce has been very influential. And to a lesser but still important degree, the bulk synchronous model of distributed computing, first popularized in the Pregel system. But we'll look at the MapReduce in some detail. There is an important computational abstraction where data is assumed to reside on disk. To use data, you need to move a large disk block, typically 64 kilobytes, containing that data to main memory. That suggests organizing data so that when you need one item in a disk block, you need them all. And typically, it takes more time to move data onto or off of the disk than the time we spend manipulating that data in main memory. As a result, it is reasonable to take the running time of an algorithm in the disk-based abstraction to be the number of disk IOs needed. Incidentally, the same ideas also apply at a lower level when we talk about moving data between main memory and the cache. But there, instead of disk blocks, we have the much smaller cache lines, but the ideas are really the same. Okay. One of the big ideas that comes from the disk-oriented abstraction is the B tree, an idea developed by Rudy Beyer, shown here. Think of a B tree as a balanced search tree whose nodes are entire disk blocks. To understand B trees, start with the better-known binary search tree. There, nodes of the tree consist of two pointers to the left and right children and a single value that separates the two children. That is, the left child takes you only to smaller values and the right child takes you only to larger values. In a B tree, each node being a complete disk block has room to store thousands of pointers to children and values that separate what can be found at each of the children. As a consequence, even a three-level B tree can store at least billions of values, possibly a trillion values. I won't go into how you keep the tree balanced, but if you know how 2-3 trees work, it's a generalization of that. In particular, you can't assume that each node will be completely full of pointers and separating values, but you can guarantee that it will be at least half full at all times. Okay, the most important use of B trees is to implement a dictionary. First, it is quite reasonable to store the root of a B tree in main memory. Okay. If we do so, then lookup in a three-level B tree requires only 2 disk IOs. And to insert or delete, take at most 3 IOs, the extra IO being to write the revised leaf block back onto disk. Now, in order to keep the tree balanced, it is necessary occasionally to modify the structure of the tree and use some additional IOs, but this extra cost is typically negligible. Now let's talk about the relational model, which is due to Ted Codd, pictured here. Okay. The data model portion of this abstraction is simple. Tables with sets of rows, so the order doesn't matter, and named columns. For example, here we see 2 relations. The first, named cities, has columns for a city and the state where the city is located. And yes, Al, I do know that Canada calls them provinces, not states, but the idea is the same. For example, the first row says that Toronto is a city in the state of Ontario. The second relation, called states, has 3 columns: state, the country in which the state is located, and the population in millions of that state. For example, the first row of the relation says that California is a state in the USA and has a population about 38.5 million. But an abstraction is more than just a model of data. Okay, it requires some sort of programming language. Now, Codd could have viewed the relational model as what we call the second type of fundamental abstraction, like trees or graphs, where the programming language consists of a set of small steps, like given a row and column, find the value there, or given a row, find the row below. This language could then be embedded in a general purpose language. In fact, prior to the development of the relational model, the database world used abstractions of exactly that kind. Called the network model and the hierarchical model. Fortunately, Codd instead viewed the relational model as a declarative abstraction, and I think this choice is the reason for the widespread use of data management systems today. So what is the programming language for the relational model? Well, that's a little trickier, and it depends on what year it is. So Ted Codd started us with 3 programming languages: relational algebra and 2 versions of a relational calculus, and all 3 were equivalent in what they could express. Then the first version of SQL, Don Chamberlain, pictured here as the leading figure, it came along and added a few more elements. Relations could be bags or ordered lists. And in addition to the relational algebra operation, there was grouping and aggregation. For example, we could take the states relation, group the rows according to their country value, and then sum the population within groups to get a new table that gives the population of each country. The work on Datalog, a more powerful logic language, added recursion to the original Codd language and eventually to the SQL standard. Now, I want to go over quickly what relational algebra looks like. It has 5 operators as listed here. The first two, union and set difference, applied to the rows of two relations with the same column name, should be obvious. But let's take selection. Selection it takes as arguments a relation and a condition involving the column names of that relation, and it produces a new relation with only the rows that satisfy that condition. For example, if we apply the condition that the population of the state is at least 20 million to the relation states, we get a new relation that eliminates these three rows. Projection takes a relation and a subset of its columns and produces a new relation that eliminates the remaining columns. Then, since relations are sets, duplicates are then eliminated. Okay, for example, if we project states onto the column country, we first eliminate the state and pop columns, and then eliminate all but one occurrence of each country. The join operation, well, takes two relations and a condition involving the columns of these relations. The result of the join is a new relation that has rows constructed from each pair of rows, one from each of the two relations, if that pair satisfies the condition. As an example, we're going to join the two relations, cities and states, on the condition that the state values from each of the two relations are the same. So here are the two relations. Since each has 6 rows, there are 36 possible pairs in the result. But what happens is that each state that appears at all appears in exactly one row of each relation in this case. So we only get the 6 rows in the result that is suggested here. For example, the row Toronto, Ontario from cities pairs only with Ontario, Canada 14.57 from states. And it yields an output row, Toronto, Ontario, Canada 14.57. Technically, Ontario should appear twice, but when the condition is equality of two columns, it is conventional to show these columns only once in the result. Note that in this simple example, each row of one relation pairs with only one row of the other. However, there could be many pairings for each row. For example, if we had a complete listing of cities, then the cities relation would have many rows for cities in Ontario, and each of those rows would pair successfully with the one Ontario row from states. Okay, just to emphasize the point about optimization being essential in a declarative abstraction like the relational model, remember that conventional languages have optimizers, but at least on a serial computer, these optimizers don't make more than maybe a factor of 2 difference in running time. Okay, for example, if I write a bubble sort program in C, the compiler won't change it to the faster quick sort because it's undecidable whether I've written a program that sorts in the first place. But when you optimize relational algebra expressions, there is an opportunity to make your algorithm run orders of magnitude faster, especially on large data sets. The fact that relational algebra is not Turing complete offers us an opportunity to understand what a program is doing, and we are able to exploit that opportunity well. So let's take as an example finding the population of Mumbai's states. If you write the query in SQL, the plan is that is implied by the semantics of SQL is first you join the cities and states relations, and then select in the result only the row for Mumbai. That gives us the population of Maharashtra and the correct answer. But when we're taking the join of 2 huge relations, we need only one row of the result. A better plan, which all database management systems today will discover, is first to select for the Mumbai row in cities and get that the state is Maharashtra. Then select again in states to find the row for Maharashtra and get its population. Essentially, if we organize the two relations in a suitable data structure, for example, hashing cities on the city value and hashing states on the state value, then this plan can be executed really fast. Now, let's look at one last example of an abstraction important in the big data world, the MapReduce, the brainchild of Jeff Dean and Sanjay Gemawat, who are both pictured here. This is a computational abstraction whose underlying machine is a computer cluster. That is, we can assume many independent processors are available, they can communicate data, but that communication is not free and may even be the principal cost if lots of data needs to move among machines. The data model is sets of key-value pairs. Keys are not unique, but just think of them as the first two components of the pair. The programming language is a conventional language, but it is organized as two programs called map and reduce. The power of MapReduce comes from its ability to exploit parallelism without requiring the programmer to think about the complexities of writing parallel code. The programmer has only to write the two serial programs map and reduce. Okay. The MapReduce runtime system starts by applying the map function to every input pair. The map function is constrained to produce only key-value pairs, but the types of the output pairs can be different from the type of the input pairs, and one input pair can produce any number of output pairs. Then behind the scenes, all the pairs that are output from all the applications of the map function are sorted by key and organized into new pairs whose first component is a key, and the second component is a list of all the values associated with that key. Finally, the reduce function is constrained to take such key list of values pairs and produce new key value pairs, perhaps of a different type. The final output is the union of all the key value pairs produced by all the applications of reduce. When designing MapReduce algorithms, there are a number of issues that we need to consider. An obvious one is the wall clock time, that is the time it takes the job to finish. But since a job can run on many machines or on few, we should also consider the cost of renting the needed hardware, that is, the wall clock time multiplied by the number of machines used. Then, especially when the map function generates many pairs from a single input pair, a communication cost can become a bottleneck because they all need to be sorted behind the scenes. There are interesting trade-offs you can make in algorithm design if you focus on the total communication required by any given algorithm. Another interesting issue is the number of MapReduce jobs needed to solve a problem. In principle, you can always do things in one trivial job that simulates a serial algorithm. But if you constrain the algorithm in certain ways, for example, by requiring that only a vanishingly small fraction of the data appear on any machine, then you require a succession of jobs to solve a problem, and the minimum number of jobs becomes an interesting theoretical issue. So I want to close by suggesting that there are still some interesting problems in the creation of abstractions for dealing with large-scale data. A number of these are motivated by new hardware platforms. One type of platform involves the use of hardware accelerators, either by themselves or in combination. For example, you're probably familiar with graphics processing units or tensor processing units, and there are other interesting chip architectures that are coming along. Then on a larger scale, an architecture like serverless computing, where your data lives only in a file system and not at processors, and you rent processors cheaply for short times to do specific tasks, is becoming popular, and probably for more than mining Bitcoin. So I propose examining whether there are good abstractions analogous to MapReduce or Pregel-say that enable us to easily take advantage of these architectures. Thank you, and now back to Al.
Hello again, this is Al Leho. I'd like to present a few unusual abstractions in quantum programming languages, because these abstractions are vastly different from abstractions in traditional programming languages. I will begin by reviewing the four postulates of quantum mechanics, a fundamental theory in physics developed in the early part of the 20th century that describes the physical properties of nature at the scale of atoms and subatomic particles. From these postulates, we can derive the abstraction of quantum circuits, one of the key models of computation underlying quantum programming languages. I'm going to follow the treatment of quantum computation as presented in Nielsen and Chung's classic book, Quantum Computation and Quantum Information. The first postulate says that the state of an isolated physical system can be modeled by a unit vector in a Hilbert space, which is a complex vector space with an inner product. From this postulate, we can derive the notion of a quantum bit called a qubit, which is a unit vector in a two-dimensional Hilbert space. The state of a qubit can be represented by a linear combination of the computational basis ket0 and ket1, where alpha and beta are complex numbers such that the sum of the squares of their absolute values is 1. The symbols surrounding, the brackets surrounding symbols are used to denote vectors. They're called kets, and they were devised by Paul Dirac with his bra-ket notation that is routinely used by physicists in quantum mechanics. Ket0 represents the unit vector 1, 0, and ket1 represents the unit vector 0, 1. These two vectors are computational basis vectors of a complex two-dimensional Hilbert space. A qubit exhibits a quintessential property of quantum mechanics. Its state is a superposition, a complex linear combination of two basis states. Postulate 2 says that the evolution of the state of a closed quantum system can be described by a unitary operator. For the purposes of this talk, you can think of a unitary operator as a complex square matrix whose rows and columns are orthonormal. A unitary operator represents a rotation of the state vector in Hilbert space. The single qubit Hadamard operator is a useful unitary operator that appears in many quantum algorithms. If we apply the Hadamard operator, represented here by this square matrix, if we apply the Hadamard operator to the basis vectors ket0 or ket1, we will get a quantum state which is a superposition that, if measured, will yield a classical bit 0 or a classical bit 1 with equal probability. Used this way, the Hadamard gate is a perfect random number generator. The 2-qubit controlled knot operator, C0 for short, is also used in many quantum algorithms. It has two inputs, a control qubit and a target qubit, and it flips the value of the target qubit if the control qubit has the value 1. Postulate 3 says the only way to get information out of a quantum system is to measure it. A measurement returns an outcome with some probability. The sum of the probabilities of the possible outcomes is 1. Measurement is not a unitary operator because it collapses the state of a quantum system. And there are many different kinds of measurements. As an example, let's consider the projective measurement of a single qubit psi in the computational basis ket0, ket1. You would like to get an amplitude of psi as an outcome, but in the world of quantum physics, you can only get one classical bit, a 0 or a 1, as an outcome. The probability of getting a 0 is the absolute value of alpha squared, and the probability of getting 1 is the absolute value of beta squared. And if the outcome is 0, the state after the measurement is ket0, and if the outcome is 1, the state after measurement has collapsed to ket1. We will use the meter to represent a quantum measurement gate. The fourth postulate says that the state space of a composite quantum system is the tensor product of the state spaces of its component systems. Here I've shown that if you take the tensor product of two-dimensional vectors, then the tensor product is a 4-dimensional vector. And if you take the tensor product of 3 two-dimensional vectors, you get a vector that is 8-dimensional. What this says is that if we combine n single qubit systems, we get a composite system with a state space of dimension 2 to the n by taking the tensor products of the state spaces of the n single qubit systems. Note that if we combine 300 single qubit systems, we get a state space with more dimensions than the number of atoms in the universe. We are finally ready to introduce quantum circuits, a key abstraction for quantum computing. Quantum circuits are sometimes called the gate model of quantum computing. Quantum circuits are a little bit like Boolean circuits, but there are important differences. A quantum circuit is an acyclic graph consisting of lines connecting unitary operators and measurement gates. No fan-in is allowed because the logical OR operator is not unitary. And no fan-out is allowed because in quantum mechanics, it is not possible to make a copy of an unknown quantum state. This is the so-called no-cloning theorem of quantum mechanics. Here is a simple but important example that illustrates what a quantum circuit looks like. It has two input lines, X and Y. The X line is connected to a Hadamard gate, and its output is connected as the control of a C0 gate, and the Y goes directly as the target to the C0 gate. When the C0 gate is applied, this is what happens to inputs. The input ket00 gets mapped into the output ket00 plus ket11 divided by the square root of 2. And the output state here is an example of an entangled state, one that cannot be written as a product of two basis states. That is a tensor product of two basis states. This quantum circuit generates what are called the Einstein-Podolsky-Rosen states. And these states have and sometimes they're called Bell states. And these states have a remarkable property. Let me just illustrate one remarkable application of an EPR state in an application that's called quantum teleportation. Here is a scenario between Alice and Bob. Suppose Alice knows that she's going to get a secret qubit in the future whose state she needs to convey to Bob. and Bob is moving far away. But before Bob moves away, Allison and Bob generate, using this previous circuit, an entangled pair. Later, Alice gets her unknown qubit. She applies a C0 gate and to the unknown qubit, and the output of her entangled half of the EPR pair. And then she takes the output of the control line and runs it through a Hadamard gate, and then runs the two outputs through measurement gates and sends the two measurements as classical bits, zeros and ones, to Bob. Bob uses these classical bits to apply to his half of the EPR pair. And what he does, he applies a conditioned NOT gate conditioned on the classical bit, and a conditioned poly Z gate conditioned on the classical bit. And if one goes through the math, one discovers that the output of the poly Z gate after these operations has the same state as the unknown qubit that was delivered to Alice. But when Alice processed her qubit, she collapsed the state of it, so she doesn't know what the state of it is anymore. What's interesting about this result is that the state of a qubit psi has two complex numbers in it, but yet Alice just sends two classical bits to Bob. By using those two classical bits and his half of the EPR pair, he's able to reconstruct the state of the secret qubit. So not only is this mathematically verifiable, but this experiment has been conducted over and over again, and it experimentally verifies the phenomenon of quantum teleportation. Teleportation has been carried over 1,000 kilometers in some of these experiments. In 1994, quantum computing received an enormous boost when Peter Shor at Bell Labs published an algorithm combining a classical computer and a quantum computer to factor integers with a polynomial number of operations. Many of today's encryption schemes, like RSA on the internet, assume factoring large integers is computational prohibitive. But if we could build large enough quantum computers with error correction, encryption schemes like RSA would be easy to crack with Shor's algorithm. But for the time being, no polynomial time algorithm is known for factoring integers on a classical computer, and we cannot build large enough quantum computers to factor the sizes of integers used in RSA, so RSA is safe for now. However, as a precaution, NIST has recently initiated a process to solicit a proposal for developing cryptographic systems that are secure against both quantum and classical computers. Several companies like Google and IBM have already built 50 to 60 qubit quantum computers, but to implement Shor's algorithm with full fault tolerance and error correction will require 1 million or more qubits, and it is not clear when such large-scale quantum computers will become available. From a theoretical point of view, if we could prove factoring integers cannot be done in polynomial time on a classical computer, then Shor's algorithm would disprove the extended Church-Turing thesis, which states that any physically realizable digital model of computation can be efficiently simulated on a Turing machine. Scalable quantum computers are still in their infancy, but our abstractions and algorithms for constructing compilers for quantum programming languages are now still viable. A little while ago, Christus Foray, a graduate of Princeton University, came to Columbia as a PhD student to study quantum computing. After taking my compilers course, she did her PhD thesis on compilers and design tools for quantum computing. Krista showed how quantum fault tolerance and error correction could be incorporated into the compiler framework we discussed earlier. After graduating from Columbia, Krista joined Microsoft Research, where she is now general manager of quantum software. A few years ago, she and her colleagues at Microsoft created a quantum programming language called Q# that is now part of Microsoft's quantum development kit, which can be used to experiment with quantum algorithms and design tools. Q# is one of 15 quantum programming languages listed on Wikipedia's quantum programming page. In conclusion, I would like to say quantum circuits are a key abstraction for existing quantum programming languages. I'd also like to say there are substantial open problems remaining in creating useful quantum algorithms and in building large-scale quantum computers before quantum computing becomes ubiquitous. Thank you.
Well, thank you, Jeff and Al, for those really insightful talks, which not only gave me experience through history, but forward-looking as well. Maybe our first question, Al, relates to this issue of quantum computing. Just as you made a case for computational thinking and teaching computational thinking, when are we going to have to start teaching undergraduates and maybe even high school students about the ideas behind quantum?
Well,
that question.
if I may jump in here, my undergraduate degree was in engineering physics, and we had a very, very brief exposure to quantum mechanics. When Krista became my graduate student, my agreement with her was that if she teaches me quantum mechanics, I'll teach her compiler design. And I'm still learning quantum mechanics. So the reason I chose quantum mechanics as an abstraction to talk about is to demonstrate what a broad spectrum of abstractions computer science deals with. And in the programming language arena, since programming languages are often the vehicle by which we implement algorithms, the field of computer science has been broad and is getting broader and broader all the time. So I think as educators, we have to be very careful about what we choose to present in our curricula, both for non-computer scientists and for computer scientists. And I think it's a very important question to ask. What should we be teaching, both in STEM education and in education more broadly through K through 12? This, I think, was part of the thesis of Jeanette Wing's article of we should revisit what we teach.
Yeah. Jeff, we have an interesting question about the point you made about declarative abstractions not being Turing complete. And the question is, if you take something like pure Lisp, for example, you might argue it's a declarative language and yet it is Turing complete. So maybe you could clarify what you mean by this.
Oh, well, no, I don't deny either of those two statements, but I would deny that you can get orders of magnitude optimization compiling Lisp the way you can for SQL. And again, when I talk about SQL, modern SQL, because it can hook to a conventional language, is itself Turing complete. But when we talk about the optimizers that are built into a database management system, it's really only working with the subset of SQL that's kind of looks like relational algebra with maybe a few more operations thrown in, so that it is a non-complete subset that's being optimized.
Al, we have a question about what your prognosis is for using AI, in particular ML, as a way to build compilers in the future and do the translation. What do you think about this prospect?
This is a great question. And as I suspect many people in the audience know, people are experimenting with using machine learning and AI as a code generation technique. In fact, one can sort of say that machine learning is another way of creating a program from data, where the data is a training set. So where this goes is up for question, because the kinds of programs that we deal with, like operating systems or compilers or substantial systems, I think are beyond the capability of what we can describe to machine learning systems currently. But the only comment I have, this is an exciting area of current research, and watch the space.
Mm-hmm. Mm-hmm. Good idea. Jeff, we have an interesting question from a mathematician here who asks, can we formalize the notion in mathematics of what an abstraction means to computer scientists?
Okay. You know, I've actually tried to wrestle with that. Essentially, the question, you know, when is something an abstraction? I think it's a good question, possibly a good research question. In fact, when an old friend was actually sent me an email yesterday talking about, you know, is this an abstraction? Is that an abstraction? And you know, so the answer is again, my hypothesis, and it's only a hypothesis, is that you've got to have in order to be an abstraction in computer science, you've got to have both some data component and a computational component. But to formalize that to the point of let's, I'll give you some notation, and you tell me whether it is or is not an abstraction. I'm not up to that point yet, let's say.
Al, somebody asked about the notion of these programming assistance systems like Copilot that helps write ML programs, for example, or AI programs. How do you see these sorts of things evolving in terms of leverage for the programmer versus actually improving the efficiency and the compilation process?
This is another great question. And as I'm sure you're more than well aware, code optimization is one of the most difficult and most interesting aspects of compilation. And if we look at modern compiler frameworks like LLVM, it has a very extensive optimization phase where scores of optimizations can be applied to the intermediate representation to try to transform it into a form from which better target machine code can be generated. Now, people have been experimenting with, from my understanding of these systems like Copilot, where you can use some description even from the comments of what you're trying to do and attempt to generate code from the comments. And for many decades, people experimented with and thought that maybe English would be a good programming language. But I'm sure that you're well aware that these efforts of using English as a programming language have failed. But on the other hand, in the last decade or so, people have produced things like low code and no code programming environments. And if one looks at quantum computing, the programming languages like IBM's QuizKit, you create a quantum algorithm by a graphical user interface where you paste quantum gates onto the screen to create a quantum circuit. So I think we're, if I may quote something that you and your colleague Patterson said, we're still in the golden age of programming languages and compilers, because we haven't written the final chapter yet of how it's best done.
Yeah, very good. Jeff, when you think about abstractions in database, this question really gets to the heart of how close the abstraction has to be to the hardware to really reflect efficiency issues. So think about memory versus disk. But of course, now in modern disk systems, there's lots of caching that occurs. Even before you get to the CPU, it occurs right at the disk level. So how much does the abstraction have to really match the hardware to give you the key insights you need from a programming viewpoint?
Yeah, well, actually, I mean, one of the interesting things is the same ideas we studied, for moving disk blocks to main memory. That's the same process that goes on when you move a cache line to a cache, and I don't know, you probably know, I don't know, maybe there are several levels of cache that where the same phenomenon comes in. The abstraction, the idea of you have something like a disk block that moves to a lower level of memory and back, does influence algorithms in at each of those levels. If you look at the most recent Dragon book, again, this is mostly thanks to Monica Lamb, there is a lot of discussion about essentially cache line aware optimization algorithms for doing things like array processing. Again, the question was, okay, how aware do you have to be? Yes, I mean, if for example, the transfer of a disk block were essentially an instantaneous operation, you have to be aware of that and stop using the model, let's say the B tree type model that I discussed. Yes.
Al, when you talk about quantum, how do you see quantum and conventional computing merge? Certainly not everything's going to become quantum, especially with the challenges of building quantum hardware. How will those get merged together in an effective way?
Well, again, there's a lot of misinformation about quantum computing in the popular press. Mm-hmm. The first observation to make is that we're very unlikely to have standalone quantum computers. All of the quantum systems that we have today are hybrid systems consisting of a classical computer controlling a quantum computer. There is another problem with quantum computing is that if you want to do, say, floating point operations, floating point is not a unitary operation. So you have to simulate floating point with quantum operations of some kind. So the current quantum systems often attempt to do optimization problems of certain kinds. There are many different hardware technologies that are being explored for implementing qubits and quantum systems, ranging from trapped ion systems to transmons to various other exotic technologies that the physicists are talking about. And you asked Jeff, what about optimization? How much do you have to know about the target machine in order to optimize? Well, some of the optimizations that you can perform on the physical operations language for these different technologies are vastly different. So it's still very much of an open problem as to what kinds of optimizations we want to perform for a given quantum technology, and how much of that optimization does the programmer need to be aware of in order to be able to do this. So I think the phrase that I like to use is that quantum computing is still in its infancy, and it's going to be a long time before we have scalable quantum computers. I might also point out that if you want to implement Shor's algorithm with full error detection and fault tolerance, you're going to require millions of quantum bits. And at present, well, I see IBM just announced a 65 qubit quantum computer. Google has one in the 50 or so qubits. So we have still a long ways to go before we can get quantum computers that would be able to run algorithms of the complexity of Shor's algorithm. So the mathematics is interesting, but the comment I like to make is that our compiler framework is good enough to be able to create quantum programming languages. We simulate them on classical computers, but we're waiting for the hardware people to catch up.
We need the Moore's law for quantum computing to happen. So, Jeff, we had an interesting question about abstraction. Given the amount of errors that still exist in software systems, including compilers, by the way, are there things we could do on the abstraction side to make our abstractions better to reduce the probability that we're writing erroneous software?
Ouch. That's a good question. I wish I had an answer to that.
That's why I asked you that question.
Yeah, right. I mean, just take that on the fly. You know, well, I guess one thing that let's say high-level abstractions, I think, do reduce the rate of bugs. If you're writing 3 lines of SQL code that translate into 10,000 lines of C++, you can still have a bug in that SQL, but it's still only 3 lines, and you know, if your error rate is, you know, whatever it is, 10% per line or something, your chances are you have reduced by using a high-level abstraction. You really do reduce the total number of bugs. You know, and nothing of this, you know, I think would be a very interesting question to think about abstractions that make it harder to have bugs. One of the things that many years ago I got interested in the programming language ML, not machine learning, but and the interesting thing about it, because it's strongly typed, it didn't it didn't reduce the number of bugs in my code, but it turned semantic errors into syntax errors, and those of course tend to be easier to figure out, you know, track down and debug. So I don't know, maybe that's a good direction to you know, to think about is providing abstractions that that make it easier to detect the bugs rather than reduce the number of bugs. Well, if anybody's got any ideas for that, please.
If I may make a comment on this, I recently heard a talk by Leslie Lamport, and he said that one of the features of having the right abstraction is that at the beginning, you have a model for what the right behavior of a system is. So rather than slinging code at the problem, you should first think about what the right abstraction for your problem domain is. And then if you get that right, you have a better chance of having a good system.
It's a good point. We've had an interesting question. Given the massive size of the World Wide Web and how much data is out there, and the fact that there's probably a lot of interesting things you could discover if you could bring that data together somehow. But of course, that's computationally not and cost prohibitive. Are there ways we could build systems that would work in an even more distributed fashion than something like MapReduce, I suppose, that could actually do computations in a broad way across the net that would be efficient in some way? How about you, Jeff? Any thoughts? You talked about MapReduce.
Yeah. Well, in a sense, search queries do already, in principle, are going over the entire net. And is it efficient? Well, you do get your answers pretty quickly. Could we do more? I assume that the question is really thinking about more interesting, you'd like to find all the data sets, I don't know, that are dealing with weather and combine them to determine whether you're going to have a hurricane in your backyard 2 weeks from now, and do that. First of all, I would say first try doing it, and then we'll try to do it efficiently. Once you have an algorithm that works, again, if you have a model in which that, or an abstraction in which that algorithm is implemented, you can then start thinking, almost as an independent problem, you start thinking about how you optimize that. That was certainly the history of the relational model was like that. First, people said, hey, we can write programs in this model and they're useful. And then they started thinking about, yeah, but some of the programs are kind of crappy, and what can we do about them? And it's been, for 20, 30 years, people were actually thinking about different ways to optimize, let's say SQL or relational algebra. So yeah, I think it's a great question to try to write, do applications that in some sense bring together unrelated data from the web or any other source if you have them, and then we'll think about optimization.
So I want to ask the last question of both Al and Jeff, and it has to do with the Dragon book. And Al, when you were writing that book, did you expect that it would have the broad impact? You've educated tens, if not hundreds of thousands of students with that book. Tell us about how you feel about that and what your expectation was.
Well, I didn't have any expectations of what impact the book would have on the outside world. My main expectation was I wanted to codify what Jeff and I were learning about the theory of compiler design. And I think it was Jeff who said that, it was Richard Hamming, who was at Bell Labs, who said that if you want to have real impact as a scientist, you need to teach others how to practice your research. And there's no better way to teach others how to use your research than to write a book. So that sort of got me interested in, well, let me try writing a book. And at that time, I was also teaching a compilers course at the Stevens Institute of Technology. So the book started out from course notes that I was using. And I was also very impressed with Knuth's dictum that the best theory is motivated by practice and the best practice by theory. And as Jeff mentioned, theory and practice are two sides of the same coin in compiler design and in the design of programming languages. So it was a great area in which to practice this dictum. So I was very lucky to enter this field when it was still relatively new and there were all these fundamental questions that were easy to answer.
So Jeff, I want to ask you about the origin of the dragon and how you convinced the publishers. Your earlier book, needless to say, had a very formal cover on it, The Theory of Parsing, Translation, and Compiling. And the dragon book, everybody knows it as the dragon book. So how did you persuade both your co-author, Al, and the publishers to allow you to do what was at the time certainly an adventurous cover for a textbook?
Okay, well, I don't know. Al, I don't think had too much trouble buying into it. Actually, I must admit it was not an exactly original idea. I mean, the dragon maybe, but I happened to notice. I guess I was in the Princeton bookstore. Must have been obviously sometime prior to our writing the dragon book, and I noticed a book that was actually self-published. Something you didn't really do these days, and it had a weird cover. I can't remember what it was, but it was two elephants holding up a sign that said "All the way with Gauss Bonnet," and I have no idea what that means. It was and that's really what put the idea in my head that that you could have a funny cover on the book, and that it might actually be an advantage. Now, of course, we weren't self-publishing, so we did have to get the publisher in. Bill Greener, who was our editor at the time, I don't know, maybe he wasn't paying attention, or maybe he had a sense of humor or something. And he basically he agreed to have the artists do something for us. I thought pretty good. And he says, right after the book was published, the president of Addison Wesley found out about this and came into Greener's office. This was Greener telling me, this is either, he said, this is either the best cover we've ever done or the worst. And I think it's the worst. And then Greener said 3 months later, when he saw the sales of the book, he came in and said, okay, it's the best. And
well, that's a great story to conclude with. Thank you both for your lectures and for responding to the questions from the audience, and congratulations on winning the Turing Award to both of you. It's well deserved.
Thank you very much.
Thank you, John.
Bye.